Good morning, friends, and welcome lecture on analysis of Pelton wheel turbine. So, in last lecture, we have discussed about the details of three types of turbine: Pelton turbine, Kaplan turbine, and Francis turbine. Now, in future series, we are going to discuss about the analysis part of these three turbines. So, in this lecture, we are going to cover the analysis part of Pelton turbine. It includes the velocity triangle of the Pelton turbine, the design related formulae required for the Pelton turbine, and two examples that we are going to take for understand for so that we will understand the analysis of Pelton wheel in better way. So for the Pelton turbine, everybody know it is an tangential flow impulse turbine. So therefore, the velocity coming from the jet is striking on the bucket and it is in tangential direction. So it is tangential to the blade velocity. Hence, this velocity will not have any kind of vertical component. So we know that for a velocity coming from the jet, that is V1, is having two components. One is vertical component and another is here horizontal component. So as vertical component for V1 is absent, therefore we can say that Vf1 is equal to 0. And this Vf1 is equal to 0, therefore Vw1 is equal to V1. So here we can say that this is now I will explain you the velocity triangle of the Pelton wheel turbine. So this is a hemispherical bucket, or you can call it as a hemispherical vane of the Pelton turbine. So this portion is there. So here this portion C at the point C, it is called as splitter. So this splitter splits the jet in two ways, two parts. One is going in this particular one side and this another going in the downward side. So here V1 is having, so V1 is equal to Vw1 because Vf1 is equal to 0. And at the same time, now we say that the blade or the vane is also moving with some velocity that is called as U1. So this will be U1, total component will be AC will be V1 and AC is equal to Vw1 because there is no vertical component for V1, that is Vf1 is equal to 0. And this AB represents some velocity, that is their bucket is having some velocity, that is U1. So this U1 is there. So U1, then BC, the remaining component. So this is called as what? Relative velocity component at inlet, that is VR1. So it is difference now in between V1 and U1. So for the Pelton turbine, now we can say that VR1 is equal to V1 minus U1, then V1 is equal to VW1, VF1 is equal to 0, and U1 is equal to tangential velocity of that particular bucket. And this velocity is equal to U2 also. So U1 is equal to U2 is equal to, we can say U. We can see this afterwards. So afterwards, this after doing striking this on this splitter, the jet deflects in two ways. One is going from this end and another going from this end. And this jet afterwards, it is going to be deflect in this direction. So this is going to be deflecting. So this is this angle. This jet is deflecting, and this is the angle of deflection. Okay. So, and from this angle of deflection, this velocity component at outlet velocity triangle. So this represents, so suffix 2 are the parameters for the outlet velocity triangle. So V is coming as a VR2, then V2, again I told you there, now V2, absolute velocity at inlet or outlet, they are having two components always. Vertical component is Vf2 and the horizontal component is Vw2. So this Vw2 is responsible for making the whirling action of that particular turbine, and Vf2 is responsible for the flow action, flow to make the flow of the water through the turbine. So this is Vf2, this is Vw2, this is V2, and whatever the V2 is making angle with the tangential direction, that is U2 direction, that is called as beta. It is called as what? Vane blade angle at outlet. And VR2 is making angle with this particular U2 or tangential direction, that is called as here vane angle at outlet. Okay, so this is going to be the triangle. So this triangle is very much important important in the analysis of Pelton wheel. So everybody should understand this particular Pelton velocity triangle. Then and then only we can analyze or we can solve the numericals on Pelton wheel turbine. So as we look the inlet velocity triangle, as the flow is tangential, it looks like a line only. So, but properties of that particular triangle we should know. Next, we'll go for the design of Pelton turbine. So, design of Pelton turbine, it's required. It's nothing but what? Calculation of the diameter of that particular wheel, diameter of jet, then calculation of the hydraulic efficiency of the turbine, calculation of output power. Then sometimes we have to calculate the angles. That includes the design of Pelton wheel. So, for the design of the Pelton wheel, already I have discussed that from inlet velocity triangle, Vf1 is equal to 0, V1 is equal to Vw1, then VR1 is equal to V1 minus U1, and outlet of the triangle, we can use some trigonometric relations. Also, the jet ratio is there. So, jet ratio is defined as the ratio of pitch diameter of the wheel or runner diameter to the diameter of jet, and it is calculated by the formula d by d. The speed ratio is their velocity of wheel to the velocity of jet is nothing but what? Velocity of wheel is nothing but what? Tangential velocity u upon velocity of jet is v, and v is equal to inlet velocity, that is v1. Then this v1 is equal to square root of 2gh. Then velocity of wheel, I told you that blade wheel is rotating at the same speed at inlet and outlet, so it is common speed. Therefore, we can say u is equal to u1 is equal to pi dn divided by 60. Then fourth formula is there that its overall efficiency is equal to mechanical efficiency into hydraulic efficiency, or overall efficiency is also equal to what? Shaft power to the work power or runner power of that particular turbine. So shaft power is output power, and here WP is the nothing but what? Water power. So this water power we can calculate by the formula. It is a inlet kinetic energy, 1/2 mu square we can call, or it is called by another formula rho GQH, or we can call rho QGH, that formula. And shaft power we can calculate by the formula. It is rho A V1 into bracket VW1 plus VW2 into U. So is equal to, but AV1 in the physics formula, AV1 is equal to Q discharge. Therefore, rho Q into bracket VW1 plus VW2 into U. With the help of that formula, one can calculate the shaft power of the Pelton turbine. And number of buckets for the turbine is equal to what? 15 plus 0.5 into jet ratio. That is, jet ratio is here d by d, or it is also called by another notation is used for the jet ratio is m. So this is where here all parameter will come. The velocity of the jet is given by v1 is equal to square root of 2gh, where v1 is equal to absolute velocity of jet at inlet, h is available at inlet, head available for the turbine. So this coefficient of velocity can be considered as 0.98 or 0.99. Then velocity of the wheel, that is tangential, the velocity of the wheel is u is given by another formula phi into square root of 2j, where phi is speed ratio. Already we defined that particular speed ratio, and its value varies from 0.43 to 0.48. Then angle of deflection of the bucket jet through bucket is considered taken as 165 degree, and from this angle of deflection one can calculate that phi, and for that calculation of the phi, here what we have to go for? So another velocity triangle. So again we'll go to another velocity triangle, that phi is equal to this angle is going to be 180 minus the angle of deflection. Therefore, at opposite angle, the DC angle is equal to phi. So this phi is also equal to 180 minus angle of deflection. So another way we can define the mean diameter of the P diameter is given by formula U is equal to pi d n divided by 60. Therefore, D is equal to 60U divided by pi n. Then jet ratio is equal to already defined, M is equal to D by D, and for the most cases of the Pelton turbine, it is taken as 12. And number of buckets is equal to, already told, 15 plus 0.5 into M. Now we'll go for one example of the Pelton turbine. I will read quickly the numerical. So Pelton wheel has a mean bucket speed of 10 meter per second with a jet jet of water flowing at the rate of 700 liter per second under a head of 30 meters. The bucket deflects through an angle of 160 degree. Calculate the power. So we have to calculate the power, then by the water to the runner and hydraulic efficiency of the turbine. Assume coefficient of velocity CV is equal to 0.98. Then for this, what is given, that first we have to understand. So u is equal to that Pelton bucket velocity is given, therefore u tangential, that is bucket velocity, u is equal to u1 plus u2 is equal to 10 meter per second. And second thing is there, that is we have to, they have given the discharge, that is q is equal to 700 liters per second. So that we have to convert into meter SI unit, meter cube per second. We have to multiply it by 10 raised to minus 3, or we have to divide it by 1000, and that will come is equal to 0.7 meter cube per second. And the head of turbine is also given, h is equal to 30 meter. Then angle of deflection is given 160 degree. Now I told you that from this angle of deflection calculation, one can calculate the phi angle. That is phi is equal to here 180 minus here angle of deflection, that is given as 165 degree. So here we can say that they are given that angle phi is equal to 180 minus 160, 20 degree. Then phi coefficient of velocity already given 0.98. So already we know that the velocity coming from that particular jet v1 is equal to cv into square root of 2j, and it will become, we put the all the value we know, cv 0.98, g 9.81, then h 30. So this will come as a 23.77 meter per second. As we know that velocity triangle, this v1 is equal to vw1, therefore v1 is equal to vw1 is equal to 23.77. Then from the inlet velocity triangle, we know that vr1 is equal to, here vr1 is equal to v1 minus u1. So from the, if you observe this particular triangle, vr1 is equal to v1 minus u1, and it is equal to 13.77 meter per second. So vr1 13.77, v1 is equal to vw1 is equal to 23.77, and then we can calculate. Then from outlet of the triangle, we have to use the trigonometric relation to calculate the vw2, and for this here, for outlet of the triangle, here cos phi is equal to, or cos phi is equal to u2 plus vw2 divided by vr2, and vr1 is equal to vr2, because the, as there is no friction, the jet is gliding smoothly on the vane, therefore vr1 is equal to vr2. Then vr1 is equal to vr2 is equal to 13.77 meter. Then vwt is equal to, if you calculate vw2 is equal to, if you use the relation, that is cos phi is equal to u2 plus vw2 divided by vr2, and therefore u2 plus vw2, that we put the substitution, then vw2 will finally will get as a vr2 cos phi minus u2, and that I all values we put, then vw2 is coming as 2.94 meter per second. Then now we got v1, we got vw1, vw2, and therefore work done, that is power required for the turbine, we can calculate by the formula, that is work done by the jet per second, and by given by the equation is given by rho a v1, but a v1 is equal to q, therefore it is rho q into vw1 plus vw2 into u. So already we know the value of rho of water is 1000 kg per meter cube. Q already we have calculated in SI unit, 0.7 meter cube per second. So 1000 into 0.7 into 23.77 plus 2 vw2 we got from this equation 2.94 into u already calculated, given in the numerical 10. So from this equation we got the power is equal to 186,970 watt. If you convert into kilowatt, it will become, dividing by 1000, it will become 186.97 kilowatt. Then we know the hydraulic efficiency formula for the Pelton wheel. The hydraulic efficiency of the turbine is given by equation eta hydraulic is equal to 2 into vw1 plus vw2 into u divided by v1 square. And here also this is the formula we can derive in the class, or we can for that separate session we can keep on this video. So this is formula. Then we know vw1, vw2, u2, v1, we can put the values, then efficiency is coming as what, 94.54%. Then another formula you will go quickly, will go through this particular through. Then this formula is that Pelton wheel is to be designed for the following specifications. What are the specifications required? So we have to calculate shaft power required to be developed by turbine is 11.772 kilowatt. Head for turbine is 380 meters. Speed required is 750 rpm. And overall efficiency eta overall is equal to 0.86% or 0.86. Jet diameter is not to exceed 1/6 of the wheel diameter. So D is equal to capital D divided by 6. Okay, determine the wheel diameter, number of jets required, and diameter of jets. So all formula we have knowing. So therefore what is given we will write here in given data. The shaft power is equal to 11.772, it is given. Then they have also given the speed ratio and velocity ratio 0.9 cv. Then h is equal to 380 rpm, that is head. N is equal to 750 rpm. Overall efficiency eta overall 0.86. Then jet ratio d by d is equal to 1 by 6. Therefore we can say that d is equal to small d is equal to d by 6. Then cv is equal to here cv is equal to 0.985, and here u, that phi is equal to 0.45. So we know that v1 after velocity component at inlet is equal to v1 is equal to cv into square root of 2gh, and it will become what, 0.985 into 2 into 9.81 into 380. Already it is calculated. Here it is 85.05 meter per second. Then here u speed ratio is there. Speed ratio u is equal to u1 plus u2, speed ratio into 2gh, and is equal to 0.45 into square root of 2 into 9.81 into 380. So it will become 38.85 meter per second. So u we know, then u is equal to that u is equal to tangential to u is equal to pi d n divided by 60. So we can convert. Therefore diameter of the we everything we know, u we know, n we know. Then we can calculate diameter is equal to 60 into 38.85 divided by pi n. So in is rpm speed is given. So from this we can get a diameter is equal to 0.989 meter. Then diameter of jet is equal to 1 by 6 into diameter of d. So it is 0.165 meter. Then here we can we have to calculate now discharge per jet. We have to calculate, so that we can calculate number of jet. So q is equal to area of jet into velocity of jet. So pi by 4 into d square into v1. So q coming from one jet is coming as 1.81, the discharge coming from one jet. Therefore, but total discharge is equal to what? From the overall efficiency calculation, we can calculate the total discharge is equal to eta overall is equal to shaft power divided by work power, and work power is equal to rho qgh divided by 1000. So from this equation we can calculate the q, and q we are getting it as a how 3.672, and discharge per jet is equal to here 1.818, and from this number of jets required is equal to what? Total discharge divided by discharge through one jet, and this is the capital Q is the total discharge divided by small q, discharge through one jet is equal to q. Therefore it will become what? 2 jets, 3.672 divided by 1.812, it is nearly equal to 2. Therefore 2 jets are required for this particular turbine. Okay, so this way some sample numerical I have taken. So in assignment I have covered many numericals, so that, and in our chapter class notes also we have covered many notes, so you are requested to practice the same. Now last article of this particular analysis we have included, that is what? Governing of turbines. So what is governing? So governing is equal to what? Governing is nothing but controlling the speed of the turbine. Why this controlling is required? Because these turbines are connected to the generators, and generators are producing electricity, and this electricity is here this speed, if the speed of the generator varies, and definitely voltage and frequency of that particular electricity is also going to be varies, fluctuate. Therefore to avoid the fluctuations of that particular electricity, here it is required that generator speed should be constant, and generator speed constant can be obtained when turbine speed is constant. And to control the speed, or to make the turbine to run at constant speed, the governing of turbine is required. So this governing is required for both turbine, impulse turbine and reaction turbine. So this governing of the turbine is nothing but what? Control of the discharge of that particular turbine, and it can be obtained by For impulse turbine, it can be obtained by spear regulation. Whatever the spear is there in that particular nozzle, spear assembly is there. So with the help of spear, we can regulate the here discharge control. Then deflector regulation is there, and combined, that is which method is there here, spear and deflector combination. That also we can use as a method for the controlling speed of the turbine. So here we can say here governing of the turbine. So it is a needle valve is there, a deflector is there, then it is going to be, so spear assembly can control the discharge. So if discharge is less, definitely power is going to be less, and turbine speed is also going to be depend on that. So discharge controlling, so we can obtain with the help of spear regulation, deflector regulation, and combined regulation. So thank you very much for listening this particular my lecture. Next time we'll cover the analysis of Pelton wheel, analysis of Francis turbine, and Kaplan turbine, that is reaction turbine. Thank you very much. Thank you.